let us discuss this theorem. Actually, this theorem is similar to the previous theorem, okay, which we have seen in last video. There is very small difference. Let us discuss it. So this theorem says when we have a matrix space XD, A is subset of X, then P belongs to A bar, that means closure of A, that means P is either a limit point of A or P belongs to A. If and only if there exists a sequence of points of A converging to P. If and only if part is there, so I am assuming first P belongs to A bar and I will try to prove the second part. Okay, so P belongs to A bar, so that means P is a closure of A, closure point of A. So therefore what can I write? So therefore for every r greater than 0, BPR intersection A is not equal to phi. So this is statement star we have. Okay, so see this definition is similar to the definition of limit point. In limit point what we do, we write minus singleton P, getting, but here when we talking about closure of A, we do not write that minus singleton P. Okay, so yeah, this thing we have. First I will put r is equal to 1, since I have mentioned initially for every r, so it is true for r is equal to 1 also. So therefore for r is equal to 1, what can I write? BP1 intersection A is not equal to phi. So if you draw a ball around P with radius 1, so this ball intersects A. So definitely we can find some point x1 belongs to that intersection. Therefore, we can choose one point x1 belongs to BP1 intersection A. Okay, I will show you here. So this is x1, one point I have taken from the intersection. See, for r is equal to half, if I take r is equal to 1 by 2, then from star what can I write? BP 1 by 2 intersection A is not equal to phi. That means if we draw open ball around P with radius half, then again intersection is not equal to phi. So again we can choose. Therefore, we can choose one point x2 belongs to open ball with center P, radius 1 by 2, intersection A. So here also we can choose one point x2 belongs to intersection. For r is equal to 1 by 3, again we will have non-empty intersection and again we can choose point x3. We will repeat the procedure for r is equal to 1 by 4, then 1 by 5. That means what we are doing, we are selecting a points from the intersection x1, x2, x3 and so on, xn and so on. So that means we are generating a sequence here xn. Okay, so see, I'm going to do that thing, but make a screenshot of it first. See, here I have written in general, if you select r is equal to 1 by n, again we will have non-empty intersection. So again we can choose one point xn from that intersection and so on. So we are generating a sequence xn, okay? We are generating a sequence xn of points of A, since each time we are selecting a point from set A, right? So we are getting a sequence xn of points of A such that each point lies in this open ball. That means x1 lies in an open ball with center P radius 1, x2 lies in an open ball with center P radius 1 by 2, and xn lies in an open ball with center P and radius 1 by n. Getting? So see, that means distance of xn from center of ball is less than its radius 1 by n. A very important thing we have. So as you can see in this diagram, we are having a sequence of points of A and which are moving towards point P. So we are going to show our sequence xn converges to P. But see, we are going to prove it using definition, using epsilon definition. So we need to take one epsilon first. Let epsilon greater than 0 be given. So I have taken one epsilon and I am going to take a help of Archimedean property. By Archimedean property. So you are familiar with Archimedean property. That means if you have any real number, 100% we can find natural number greater than that. So here also we can find natural number such that 1 upon epsilon less than capital N. We are taking a real number 1 upon epsilon. 100% we can find a natural number greater than this 1 upon epsilon. I will interchange them. So what will happen? We will have 1 upon n less than epsilon. I will call it as inequality number 2. Okay. So make a screenshot of it. Then we will go further. I have kept these two inequalities here since we are going to use them later. Okay. So now I will consider for n greater than or equal to capital N. If you take reciprocal of both sides, inequality will get changed. So this is inequality number 3. So I am going to combine 1, 2 and 3 from 1, 2 and 3. What will you get from 1, 2 and 3? D of xn p. See, d of xn comma p less than 1 by n. 1 by n less than or equal to 1 by capital N. 1 by capital N less than epsilon. So that's why this is less than epsilon for all n greater than or equal to capital N. I should carry this condition here. Okay. So let me remove this part. It is not required. Okay. And we have used it. So this is nothing but definition of convergent sequence. So therefore, sequence xn converges to P. This is definition of convergent sequence, and we can write xn converges to P. So that means here we get a sequence of points of A converges to P. So therefore, we get a sequence of points of A converges to P. So conversely we have to assume this part. We have to assume that there is a sequence of points of A converges to P, and we have to prove that P belongs to A bar. Make a screenshot of it first, then we will go further. See, now we are assuming that there is a sequence xn of points of A converging to P, and we have to prove that P belongs to A bar. So I am going to use the definition of convergence sequence here. What we have, xn converges to P. So therefore, for given epsilon greater than 0, but see, instead of epsilon I am using r here. There exists n belongs to set of natural number such that d xn comma p less than r, since we have taken r here, right, for all n greater than or equal to capital N. So since sequence xn converges to P, so that's why by definition we can write it. So therefore, xn belongs to open ball with center P and radius r. Since distance of point xn from P is less than its radius, so definitely that point lies in a ball with center P, radius r. Again, for all n greater than or equal to capital N. See, we have one more information. Sequence xn is a points of A. But I will mention, but xn belongs to A for all n belongs to set of natural number. What we are getting here, xn lies in this ball with this condition, and here xn lies in A for all n. So that means xn lies in intersection also, but with this condition. Okay, so I will write therefore xn belongs to open ball with center P, radius r, intersection A for all n greater than or equal to capital N. See, for all n greater than or equal to capital N, xn is an element of this intersection. So that means in that intersection there are infinitely many points. Getting? So see, therefore what can we write? Therefore, open ball with center P, radius r, intersection A is not equal to phi, right? Is not equal to phi. So therefore what can we say? P belongs to A bar, since this is definition of point which lies in a closure of set A. Okay, so therefore finally what we got, P belongs to A bar. So in this way we proved this theorem. Make a screenshot of it, then we will stop. Thank you, bye bye.